Okay, these are the real numbers that you have discussed before, either in middle school or in Algebra 1. To begin with, and this is not the neatest representation or a Venn diagram traditionally, to start with, you have counting numbers, which is your smallest set of numbers or family of numbers. These are the numbers that you can do naturally. These are also called natural numbers. It's your fingers and toes. Think of it that way. You begin counting 1, 2, 3, 4. It is things you can touch and put a number to. Of course, it goes all the way up to infinity. You have large counting numbers like 1,000,000, 1,551, things like that. But as long as you can touch one thing, touch another thing, put a thing with a number, those are counting numbers. This next number set right outside of the counting number, which encompasses the counting numbers or natural numbers, are the whole numbers. The only difference between whole numbers and counting numbers is the number 0. So 0 and all the counting numbers, those are whole numbers. The next set of numbers that you encountered was in middle school, when all of a sudden you began talking about the number line and you had, oh no, negative numbers. Those are the whole numbers and their opposites. So things like -2, +2, -4, +4, -529, +529. Those are integers. Integers do not have fractional parts. They do not have decimal parts. They are whole numbers and their opposites. So that would be 0 and then positive and negative numbers. Rationals you have known for a very long time. You know decimals. You know fractions. Rationals can be positive and negative. They are repeating decimals. They are terminating decimals, which means that they end, something like 1.25. They are mixed numbers, 5 and 1/2. They are proper fractions, like the 1/4. They are improper fractions, like 9/2. Repeating decimals, like 0.33333 or 0.254254, anything that has a pattern, those are rational numbers. We can express any of those as a fraction. Irrational numbers, this set that is sitting next to our rationals. Our rational numbers are also counting numbers, whole numbers, integers. We can express an integer as a fraction over 1, so -4/1, that would be rational. Irrational, you've had experience with these as well, like pi, 3.14159, and it goes on. Those are decimals that have no end, that have no pattern, they do not terminate, and there's not a repeating pattern. You keep looking at all these numbers and there's not a distinguishable repeating pattern to the digits. There's this e, base e. It's like 2.17 something, and we deal with it when we do logarithms. It's the natural base. And they are constants that we use a lot. And you run across them too. They don't have to be these constants with a standard variable that's set for them. They can be anything that you can come across, and it's a non-repeating, non-terminating decimal. This largest number family or set that holds all of these together are the real numbers. And we have talked about these when we have been looking at things like graphs of parabolas, graphs of lines, and we talked about the domain and the range. And when it is non-ending, you have this continuous graph and all the points run together, and it is all the real numbers, because you can have a point that is a whole number x and y value, or an integer x and y value. It is also those numbers in between the integer values, being decimal values in between. So it runs into everything. And now we're about to experience a new number set, the complex and imaginary number set. So here are the numbers that you have just sketched, the real numbers with all the natural numbers and the whole numbers and the integers and the rationals and the irrationals inside of them. Right next to them and also encompassing them are these complex numbers. Up to this point, you have not been able to take the square root of a negative number. And oh my gosh, now we have a definition where we can define the square root of negative numbers and define them as complex numbers, because the square root of -1 is I, and I squared is -1. And if we have this definition of this imaginary unit, we now have opened up a whole set of numbers, and we can apply our rules to them, our distributive property rules, our commutative rules, and we can graph other points. We have those parabolas that didn't cross the x-axis, and we can find all kinds of points in the complex and imaginary system. So we have the imaginary unit, which is the square root of -1. A complex number is written in the form of a plus bi, which means that you have this real number part, which is a, the bi part, which is our pure imaginary part, which is a combination of similar to a coefficient with I. So like 2i or 4i, 5i, -7i. So anytime we get to the end of a problem where we're simplifying, we make sure that we write real and then imaginary. Let's go through some powers of I, just so that we are accustomed to it and see what happens. So of course we know by definition, since the square root of -1 is I squared is -1. What happens when we do I to the third? Within I to the third, we have a pair of I squared. So I squared, and then of course if we have 3, I times I times I, we have a leftover I. I squared is -1. So I have -1 times I, and that gives me -1i. Well, let's look at another one. So I to the fourth. I had just done this. I had one I squared pair. I had this leftover one. Well, I have another one. I have I times I times I times I, so I can pair up all of my i's. So I have 2 pairs of I squared, which means I have -1 times another -1. I can square them both, which gives me a +1 answer. Let's do I to the fifth. I to the fifth, I could just reference what I had done just a moment ago for I to the fourth. I have 5 i's, so I have just one more I than when I had done I to the fourth. So I have these 2 pairs of I squared, which I had already decided was 1, plus this extra I, so I have 1 I as my answer. Okay, well, I to the sixth. I'm going to have another I, so I can pair this I up with another I, which means I'm going to have how many pairs? I'll have 3. So I'll have a -1 times a -1, then times another -1, which gives me -1 as the answer. So if I do I to the seventh, well, I can reference back to I to the sixth, but I have an extra I. So I've just done these 3 I squared, these 3 pairs of I squared, which gives me a -1 and an extra I. So I have -1i. So is there a pattern developing here that maybe I could look at and predict what will happen from now on? Let's do a couple more. I've got these 3 pairs. I had an extra I. If I do I to the 8th, that means I have one more I, so I have all of them paired up, which means now I have 4 pairs. So I squared, I times I, or -1 times -1, excuse me, would be +1, and then another -1 times -1, which would be +1, so I have an answer of a +1. If I do I to the 9th, I will have one more I than these 4 pairs, so I would have just an extra I on this +1, so I have +1i. So we were sort of beginning to see a rule developing here, or a pattern developing here. So can I write a rule for any I to the nth power? What are we seeing happening here? We have some positives and negatives. We have some i's sometimes in our answer, sometimes we don't. If I have an odd power, there will be an I in the answer. If I have an odd number of I squares, there's going to be a negative answer. I have -1i, I have -1, I have -1i. I have an odd number of I squares. If I have an even number of I squares, there will be a positive answer. So, I have some extra words here. I have I squared, I have 2 I squares, I have 2 I squares, I have 4 I squares, I have 4 I squares, so I have some positive answers. So when we do a problem like this, and I can just be obnoxious with my exponent here, I to the 363, well, I have an odd exponent, so that means I have I in the answer. It's the rule that we just kind of stumbled upon. And that means I have this extra I. So if I have an extra I, so then I can think about, instead of 363, 362. So how many pairs of I squares would I have? Well, basically that would mean I can divide this by 2, so that gives me 161. So how many pairs do I have? An odd number of pairs, so that means not all the negative ones, when I multiply them out, will end up being a positive 1 as an answer, and then the negative 1 as an answer. So I have negative 1i. Now that I have negative 1, the square root of it defined, I can do square roots as well. So I defined a while ago, negative 1, the square root of negative 1 as I. Okay, so the square root of negative 1 is I, so that's by definition. So we can use that to do any square root. So let's do any square root. If I can do the square root of 81, I should be able to do the square root of negative 81. I'm going to think of that as negative 1 times 81. Well, I know the square root of 81. It's 9. So if by definition the square root of negative 1 is I, then this is 9i. Well, if I don't have a perfect square root, then I can break this down and we should be able to rely upon what we had done in Algebra 1. So I have a negative 1 times my 32. Let's break this down into numbers that we can do the square root of. Hopefully we can think of the largest square root, but if not, let's just break it up. 32 is 8 times 4. That's fine. The square root of negative 1 is I. 8 is not a perfect square. 4 is. The square root of 4 is 2. So I have 2i times the square root of 8. But 8 I can still break up. So I have my 2i that I've already pulled the roots out, extracted those roots. 8 breaks up into 2 times 4. 2 I cannot extract a root for. I cannot do the square root of. I can do the square root of 4. So if I take that root out, if I square root 4, the square root of 4 is 2. I already have 2i, so if I multiply 2, which is the square root of 4, times my 2i that I already have, I get 4i now. This is my 2 that I could not take the square root of. So I have 4i times the square root of 2. I can also multiply using my I, my imaginary unit. What do I multiply together? Well, 4 times 6, 24. I times I kind of go along like it's an x. You have I squared. Oh, but we know that I squared is, by definition, negative 1. So this tells me right here that I have negative 1 times 24. So I get negative 24. Here I have a bunch of stuff going on. Right here, I need to square negative 3 times I. So negative 3 squared is a positive 9 because it's negative 3 times negative 3. Then I have I squared. Oh, but I squared is negative 1. So really this is saying I've got to do negative 1 times 9. So I have negative 9. And then I need to multiply by my 7i. So I get negative 63i. I can also combine like terms. So I have this binomial plus this binomial. Like terms of negative 1 and negative 2, which is the negative 3. 5i and a negative 3i, which is positive 2i. Remember to make sure that you are in your complex number form, and we are, so this is okay. We can also subtract, which, same thing, you're combining like terms. We can also distribute, same thing, you have 6 that you're distributing to both of these terms, your 9 and your 2i, which gives you 54 and 12i. You also need to distribute your negative 8i to the 9 and the 2i, which gives you negative 72i and negative 16i squared. However, this does not stay negative 16i squared. It looks like you have a variable, but remember you have defined I squared as negative 1. So you not only have a negative 16, you have negative 16 times negative 1. So if you have negative 16 times negative 1, you suddenly have positive 16. So you have like terms here, 54 and 16, which adds together to give you 70. So we have 70 minus 60i. And we do put 70 in the front because we want to make sure that we have a plus bi in that form. And we can do this problem as well. And we will begin here tomorrow. So